Now, before we talk about solutions, let's see what other kids have done. Here we have Valeria, and another kid, and another one. It's okay if you couldn't figure them all out. Look at this kid. Man, she got a lot of different answers. So the first thing I have to teach you is this thing called factorials. Now you're touching into college math here, but well, that's okay. Factorial means an exclamation mark. And what that means is you multiply the number by everything below it. So 5 factorial would be 5 times 4 times 3 times 2 times 1, right? 5 times 4 is 20, 3 times 2 is 6, and then we have multiply by 1. So 5 factorial actually equals 120. You see that? Oh wait, don't put the exclamation mark at the end of it. So let's get a little fancy now with fractions. I'm sure you've known stuff about fractions before, but now we're going to get a little funky. If I put 5 over 5, that makes 1, which means I can put anything over itself and it makes 1. So now I can use up 4 different 5s in this one. In fact, if I put anything over itself, it makes 1. But there's also some other tricks we could do. We could put 5/10 over 5, and that would give me 1/10. So if you end up with a decimal answer, you might need 1 more tenth. And then we can just do some fancy work with decimals, keep those 5s. All right, but now I got to show you this thing, exponents. Maybe you know a little bit about exponents, but we're going to get pretty weird. Now, when you were in 2nd grade, your teacher taught you if you do 5 4 times and you add it together, it's 5 times 4. But here in the upper grades, now we're doing how many times you times it, and that would be 5 to the 4th power. So it's a little bit trickier, and there's lots of different ways you can multiply 5 multiple times. You can put an X, you can put a dot, you can do parentheses, but 5 to the 4th power simply means 5 times 5 times 5 times 5, okay? And so 5 to the 4th power is actually 625. That's a big number. Now, there's this other little thing, and we can go the other way. If I take the answer to that, which would be 625, and I take the 4th root of it, I end up with 5. So now we know exponents, and now we know roots just a little bit. That weird symbol I drew, that's called a radical. And then that little 4 there, when we use it in our grades, we're going to call it an exponent. But, you know, if you use it in the radical, it's called a root. So I told you that we used parentheses. And when you see a parentheses with no operation, that just means to multiply. And I used some other operations here. There are, in fact, 4 operations that we typically use, and that's addition, subtraction, multiply, and divide. Those are the 4 main operations that we use in math. But there's other ways that we can actually think about exponents. You don't have to put an exponent above a number. Typically what you do is you can put it above a 10. And that's what scientists do a lot because they deal with very large and very small numbers. So 5 to the 2nd power means 5 times 5, which is 25. But 5 to the 10th power is 50. If I put my exponent on the 10, now I have 5 to the 10th, or 5 times 10 to the 2nd power, 5 times 10 to the 5th power. Don't forget that comma after every 3 digits. Or I can do 5 to the 15th power. You know, if you're using with astronomically large numbers, like in black holes or outer space, then, well, it's kind of hard to write all those zeros, isn't it? Don't forget the comma every 3 digits. Now that's all just kind of fancy math, but we need to stick to the basics in order to get this here. And now I'm talking about parentheses, exponents, multiplication, division, addition, and subtraction. This is the order that you need to do them all the time. It's called the order of operations. And if you do things in the wrong order, you end up with the wrong answer. So let me show you what I mean by the wrong answer. So I'm going to take order of operations and I'm going to do it in the wrong order. And then I'm going to get the wrong answer. And you're going to see what I mean. Watch this. It seems so logical, but it is totally wrong. I didn't do it in the right order. I didn't do parentheses first. I didn't do multiplication first. I didn't do addition last. I went in order from left to right. Now let me show you how to do it in the right way using the rule of the order of operations. I'm going to give you the same problem and I'm going to give you the right answer. Watch this. Always do multiplication first. Then do addition and subtraction. Wait, hold on a minute. 8 minus 42. Wait, I'm going to end up with a negative number. In case you don't know about negative numbers, let me show you what I'm talking about real quick. It's an easy concept to understand if you think of it in smaller digits. We've all been working with the number line since kindergarten, right? You get a 0 right here, and then you put a 1 and a 2 and a 3, and it goes on to infinity. And maybe if your teacher was an extra special teacher, she got you using the fractions right in the middle where they belong. And she would ask you, like, what's less than 1 but bigger than 0? Right? But now there's actually things that are less than 0. And it's kind of like if your parents have a credit card, they understand less than 0. I can owe somebody $1, right? So let's go back to that order of operations and let's look at a little closer, and I promise I won't give you any negative numbers in this one. So I'm going to start with the same digits, the same operations, but now I'm going to force which problems I want done first by adding the parentheses, because parentheses always comes first. So then this problem becomes a whole lot easier. 6. The order of operations is so important. Let me pause this to tell you a little math story. In the year 1572, mathematicians are all just sitting around making rules for multiplication and long division and all kinds of other things that are complex. And some mathematicians thought the number 0 was useless. And some thought negative numbers was useless. And then there's this thing. You see this thing? Some mathematicians of that day had a small heart attack trying to figure out what this was. It made no logical sense. So some other mathematicians made fun of them and they called it imaginary math, right? You can't even put it on a number line. You can't put it on a grid. It's not tangible. So then after 200 years of debating this, a guy named Euler and another guy named Gauss, they said, look, I know it doesn't make any sense, but it makes all our other equations work. So we either have to throw out all the other equations or we have to accept this thing that doesn't make sense and call it done. So he says, I don't know why it works, but it's a real thing, trust me. And here we are, living centuries later, and we actually use this number in a lot of ways that these guys could have never even imagined. We use this number a lot in electricity, in quadratic equations, in quadratic planes. That cell phone you keep using, it uses this. Okay? Wireless technology, radar, brainwaves, the list goes on of ways that we use imaginary numbers. So if you don't understand something, it's totally okay. Euler and Gauss, they prove that. Math is a puzzle, and the deeper you get into it, the weirder it gets. So, back to the 5-5 solutions, because I'm about to show you something very, very strange. So 5 to the first power is 5. Now 5 to the second power is 5 times 5, which is 25. 5 to the third power is 5 times 5 times 5, which is not 15, right? It's 125. Now we take 5 to the fourth power is 5 times 5 times 5 times 5, which is 625. Okay, this is growing exponentially. Now, when we throw in negative exponents, something very strange starts to happen. We get 1 divided by 5, which is, 2/10. And then 5 to the negative 2 power is 1 over 25, which is 4/10. Now, let's get really, really weird. Okay. If you have a solution to that one, leave a comment. Here's another one that I think you can figure out.